Hello, Third Laboratory Signals and Systems, Teacher Mario Giraldo.
Hello, everyone. This is our third laboratory from the subject Signals and Systems. This is simulation of systems described by differential equations using Simulink. So here we go. The group is conformed by Emanuel Gomez, Juliano Espina, and Camila Tonusco. First of all, we're going to talk about the first system, that is the Segway. So we're going to talk about it. First, what is the Segway? The Segway is a self-balancing personal transportation vehicle that is characterized by its two parallel wheels, a platform for the rider's feet, and a handlebar for steering. It operates using gyroscopic sensors and a computer based control system that helps the rider to maintain balance both while moving and stationary. Some features of the Segway is that it has self balancing, efficient mobility, and ease of use.
We will analyze the mathematical model. This is the equation that describes our system. We first must solve for the input to analyze it. First, we make use of the characteristic equation and the derivative operator to find its roots. We are left with three different roots for this system. The first one is the overdamped one, in which we have two negative real roots. We are solving for the friction force here because it's the force that alters the system the most. The second root we have is the critically damped, in which we have two negative and equal real roots. This b here should be just b, not the square one. So the third one is the underdamped, in which we have two conjugatives with real negative parts. Now we must solve for the greatest derivative to put this into a diagram block in Simulink. We fix our constants and we put our requirements for b. Now we put this equation into a diagram block in Simulink. Notice that each of these terms has its gain and everything is condensed in the sum. And finally, we put a different value of b for each case and we obtained a graph.
So right now we're going to talk about the graphic analysis for this problem. We have here the three types of response: the underdamped, the overdamped, and the critically damped. So here we're going to say some things about the rise time, the setting time, and the max overshoot. First of all, the rise time, we have to say that it's necessary to evaluate the speed at which a signal can change state, or the time it takes for a signal to go from an initial value, in this case is like the 10% of the maximum value, and to go to the final value, in this case is the 90% of the maximum value. So here we have like this purple line where we marked like the 10 to 90%. The setting time is the time where the signal goes to steady value. So here we have it. And the max overshoot, overdamped and critically damped are zero, because the maximum value we find it when the response is at the steady value. So that's why it's zero. Now we're going to talk about the second system, that is about viral infection dynamical behavior. We see here that when a viral particle enters an organism, it begins by attacking lymphocytes to utilize their genetic machinery. So we here see the differential equations for the problem. We declare the state variable, and forward we will see how this goes.
Here we have the block diagram for the second system. It represents a system of differential equations modeling the interaction between the infectious virus, the non-viral particles, and the infected cells. For equation number 2, we used C minus plus the integrator to obtain the variation of the infectious virus in time. For the first equation, we used K plus the target cells plus Bt minus the dead cells plus the integrator to obtain the variation of the infected cells in time. And for the third equation, we used N plus the dead cells plus Ct minus C plus the integrator to obtain the variation of non-viral particles.
Now we're going to discuss what will be an input to the system and can a state variable be an input to the system. So for the inputs, we think that the immune response activation could be an input to the system, because we can think about like external stimulation of the immune response, like could alter the rate at which infected cells are targeted and destroyed. And for the next question, typically the state variables are outputs of the systems rather than inputs. They describe the current condition of the system based on its initial state and in the input conditions. However, in some control system frameworks, state variables can act as inputs to other subsystems or processes, depending on the modeling approach. But in this model, the state variables are used to describe how the concentrations of infected cells and virus change over the time, while they are influenced by inputs. So, in this case, they cannot be inputs.
The block diagram was run in Simulink, resulting in these graphs. A timer of 20 was set to obtain a well-stabilized graph, and then each of the intrinsic parameters of the system was changed, and the results are shown in the next table. Target cells and K exhibit the greatest influence on the system response. Changes in target cells and K notably alter the concentration of infected cells and non-viral particles, making them critical for understanding virus propagation. These parameters have low variability, meaning their values cannot fluctuate significantly without affecting the system's overall behavior. N has the least influence and can vary widely without major effects. Dead cells and C have moderate influence, affecting specific aspects of the system, but not as significantly as target cells and K.
En MP3.
No le contesto, se